Okay, so I'm going to start as an introduction to looking at manifolds, start looking at how some of the results were derived for the geometry of curved paper folds. And so what I'm going to do is basically just review what we know about lines and surfaces in 3 dimensions, and then look at the specific type of surface for that is applicable to the paper folding. And then you'll see what properties we look at, and then we're going to actually see how we can say it. And then when I do the full GR version or the full manifolds version, you at least have something to hold on to try and actually something concrete, so an example you can refer to. So what we're basically going to describe is, here you have a curve on a sheet of paper, and you can fold it in a certain way, and the shape changes. There's various number of shapes that are possible with a given fold, and you can see how it's illustrated down here. Okay, so but before we do that, let's take a basic look at curves. The reference I'm going to use is actually one that, well, the way they've done it is actually possibly the best introduction to manifolds I've seen. So a lot of what I'm going to be talking about today comes from this paper. It's Duncan and Duncan, the first guys to actually work out, I think they were working on sheet metal stuff, how it folds and what it does. So it's definitely worthwhile getting it, in particular looking at the sort of the examples they've done and how they've done it, and the pictures are particularly good. I'm not going to be able to reproduce their pictures in the same way they've done it. I'm going to be using slightly different notation in the sense that it's actually going to connect more directly with the manifolds later on. But wherever possible, I try to keep the same variables and things. Okay, also this thing is on the website, the Origami website. There's a Duncan and Duncan thing there, so you can actually go and look at the Origami website. That's not the Tensor one, but it is there. Okay, so let's begin. So when we look at these curved folds in 2 dimensions, what we basically have is a curve on a flat piece of paper, in 2-dimensional one, that we're ultimately going to try and find the relationship of to the 3-dimensional curve. Now there are ways of working with curves, and I'm going to do first 2D and then 3D and look at the way we actually think about them. So most fundamentally, a curve, and I'm going to call it C bar, is a function that goes from an interval in the reals to R2. So it basically maps an interval onto R2, and a place where we find it is crease folding, but anything that's moving in a plane has that. And so there are various ways of describing this curve. You can simply say it's a function of x and y, and then you have a curve, an implicit definition of a curve. Or you can actually have a parametric definition, namely you specify the coordinates on the curve for a parameter lambda. So here we typically have lambda being in the intervals a to b, and then here we see how it is mapped onto R2 with the coordinates x and y. And so one example, I don't know if you've ever looked at an oscilloscope, is they call it Lissajous figures. It's simply those very nice patterns that they make like that, where you have 2 different frequencies interacting. And the reason I chose this example is that it's the simplest example that starts looking like the orbits in Kerr projected onto that slice. Okay, so if you look at just the rho and z coordinates for the Kerr orbits, you're going to get figures that look very similar like that than this. And it's just easy to use this example because we can actually do the calculation. And so simply, like all the orbits you guys have been looking at, and all the orbits that in fact Petrus will be looking at when he looks at the curves, the folded paper curves, they just curves and they parameterize in a way. And now an important feature that you've already come across is a little bit you can define the length of a curve C, and you did this in the second year. But one way of doing it is to say it's the integral over the interval that you're integrating from times the norm of the derivative of C. Okay, so this is simply Pythagoras in some sense. Here the derivative of C will give you dx d lambda squared plus dy d lambda squared square root times d lambda, and that will give you the length of the curve. Okay, so this should all be familiar. Then lambda can be any parameter. There's a special parameterization, and it comes here. We call it the arc length parameter for the paper foldings. In GR, you call it, yes?
Sorry, so they will define A and B as the variables just in front of x and b. That has nothing to do with the A and B in the integral.
No, sorry, there's a bad notation.
Okay.
Okay, so A and B is the interval over there, and these are constants, and those have been put to 1 for all practical purposes. So the arc length parameterization, and in GR they sometimes call it the affine parameterization. That is, you've chosen your parameter so that the parameter indicates how far you have traveled along the curve. And the way you do this is you call this new parameter S. In GR we often call it tau. And what it does, the way you define it as follows, it's basically for all lambda in A and B, we're going to define S as a function of lambda, basically as the distance from the starting point to lambda measured along the curve. Okay. And so what you can then do is consider C to be a function of S, rather that has the same value as C at lambda that has resulted in a particular S. Okay, so you're basically restructuring the parameter along the curve. And lambda of S is the inverse function of S of S. Okay. Typically, these integrals are nasty, but there are tricks that I'll show you now when I actually look at an example that allow you to work without actually working out the integral. Okay, and you've already come across some of those tricks with the Mino parameterization.
Sorry, that integral, does it go from A to lambda?
Yes.
What happens to B? Is it irrelevant?
Well, lambda is in A and B. So you literally have the parameter starting at A, going a little distance, a little bit into your curve, and then you actually measure then the new parameter S is the actual distance to that point. Okay, and this is what they call the arc length parameterization of the curve. And so what you have is for all A in AB, S is actually then a function of 0 to L, right? Because when lambda is A, it's just the integral from 0 to 0, from A to A, so that's 0. Okay, and when lambda is equals to B, it's this integral from A to B, so that's just L. Okay, so you've changed the interval from the arbitrary parameterization you started with to something that actually reflects the interval. And an important thing now is that if you work with an arc length parameterization, the derivative of C with respect to S is equals to 1. Okay, can you see that?
It makes sense, but
okay, so prove that one at your own time, but you'll see how I will go about using it in a moment. Okay, and we're also going to say S traverses the image of C at unit speed. Okay, so we've changed basically the way we demarcate the curve. We've not changed the curve. And the way we've changed the way we demarcate the curve is such that the tangent to the curve is always constant with an arc length parameterization. Okay, so now And the arc length parameterization, because of this feature that the tangent is always the unit vector then, or is always a unit vector, it makes it easier to actually get the physics out, because we're now measuring the curve with a set of specific distance that we have meaning to, and we are measuring the tangent also. It has just a unit vector size. So the properties of 2D curves is, firstly, you have the tangent vector, and now whenever I have S, I've basically assumed I have the arc length parameterization. So we have T of S equals to dc of S ds. Okay, and the norm of T is just 1. And then we're going to define another scalar, and we're going to call that the curvature, kappa of S. And that's going to be the derivative of T with respect to S. Okay, so the derivative of T is also, once again, a vector, and and its norm is simply what we call the curvature. And then we're going to have another thing that we're going to call the unit normal, right? Unit, basically, once again, it's a unit vector, and it's going to be equals to 1 over the curvature, so I'm just basically dividing by the norm of dt ds. Now, the next thing is, it's always possible to prove that the n or ns dot t of s is 0. Do you know how to do that? Huh? You want to give it a go?
Just the dot product.
So I have my tangent vector of my normal vector. Why are these two 0? Why is the dot product of the two 0?
Because they're perpendicular.
Why are they perpendicular?
Because it's a normal and a tangent vector. Yeah.
How would you prove it?
That the angle between them is 90.
Okay, so
Do we going to use the details that we have?
yes, you need to use the details that you have.
Yeah, I know.
What does this thing say? Huh?
Its size is 1.
Yeah, but its size is t dot t. T of s dotted in with t of s is equals to 1.
T dot T was within now.
Okay, so if you differentiate that, what you get is the derivative of t of s dotted in with the derivative of t of s, the full derivative with respect to s. So then you get dt ds dotted in with t of s plus t of s dotted in with dt ds. So you basically get 2 times dt ds dotted in with t of s. And the derivative of a constant is 0. So that's 0. And okay, so just let me do it on the board. So you've got you've got t of s dotted in with t of s is equals to 1. So you differentiate that dds of t of s dotted in with t of s is equals to 0, and so you have t of s, sorry, dt ds dotted in with t of s plus basically t of s dotted in with dt ds equals to 0, so you have that 2 of these are equals to 0, so you have dt of s ds dotted in with t of s is equals to 0. Okay, and the TDS is simply equals to kappa of S times n of S dot n of T of S. It's to 0. Okay, and that's where that thing follows from.
Thank you.
Okay, so now the next question is, so the answer to the first question is to simply differentiate the fact that the norm is 1. So this thing is only true if you're actually being parameterized with your arc length parameterization. Right? You couldn't say the same thing if you are not, if you're using lambda here. So you must be careful with that. You must make sure that you're actually working with the arc length parameterized curve for this type of thing to be true. Okay, so now the next thing is, can you work out what the NDS is? Or more specifically, can you work out in what direction it points?
You can try it.
Should be able to. Okay, so let me ask you another question. Any vector, how can I express that if I know, suppose I know my tangent and I know my normal. I can project any vector onto the tangent and onto the normal. Okay, so I can literally say any arbitrary vector is simply A times T plus B times N. Okay. Yeah. And so what you know is, in general, the NDS is simply A times N plus B times T, okay? But you know that N is once again a unit vector, right? Because of the definition. Therefore, N will not point, its derivative will not point in its own direction. So it will point, the NDS will always be proportional just to the tangent vector. Okay, so once again, the fact that you are using a unit normal over here and that your tangent vector is a unit vector makes these type of calculations easier. So in 2 dimensions, if you have a curve, there are basically 2 vectors that you can describe, span the whole space with near the curve. It's always your tangent vector and the normal onto the tangent vector. And if you take the derivative of the normal on the tangent vector, you get something that points back in the tangent vector. And if you take the derivative of the tangent vector, you get something that points in the direction of the normal vector, but with a certain size. Okay. And that type of game we play in higher dimensions as well.
So the NDS will point into the tangent vector, which is TS.
TS times some constant in front.
Yeah.
So now let's look at our example. So you're also going to work out your own version. And let's have a look at this curve. Okay, so we have our curve. It's parameterized with lambda because that's easy to do. So we have cos of 3 lambda, sine of 4 lambda, okay? And I've plotted it here for certain lambdas and it looks something like that. And suppose now I want to give you an idea of what the parameterization is. So suppose I put dots on there as I increment lambda in radians with 0.1. Okay, so you can simply see from plotting it like this that this is not an arc length parameterization. Okay, because this distance is much smaller than that distance. And in arc length parameterization, you can actually see the distances must be what you normally think of distance. Okay, so there's so if it's not an arc length parameterization, let's just work out what the tangent is expressed with respect to the parameters. So the tangent with respect to the parameter is just simply dc bar d lambda, and there we have it. Okay, you can just differentiate this guy, and there you get it, and that's the size of that vector. And so if you wanted to make this thing a unit vector, you would simply take this tangent and you would divide by the norm that's over there. Okay, so the norm of this big tangent is simply the square root of this norm squared. So there we have it. Another way of writing the norm is to use our definition of S. So the S d lambda is equals to C prime lambda. Okay, and remember we simply would, to get S, we would simply integrate over that over our interval to lambda. Okay, and we can do this integral, or you can try and do this integral. It'll be a lot of work. When I work with these curves, I tend not to do the integral. Okay, but whenever I do ds or dds, I tend to express that in terms of lambda itself. Okay, so instead of finding the arc length parameterization explicitly, I just rescale the vectors so that it has the correct parameterization. Okay, so you are welcome to actually do the integral and find the curve explicitly in terms of S to try it. I mean, I didn't try it because that'll work fine. But in practice, when I'm working these things out, both in GR or any random curve, I tend to stick to whatever parameterization the curve is the simplest in. And then when I want to work with my unit vectors, I use this trick that derivative with respect to S is this. And then I just know that implicitly lambda is a function of S. Okay, so if you were working in S and you would actually do this integral, you could make intervals that are arc length long, but I don't. Okay. So what I do is I still want my unit vector, right? So my unit vector T of S, this definition is just dC of S ds. Okay, and I can say, okay, fine, that is equals to dc expressed in terms of lambda d lambda divided by the s d lambda, which I have replaced by this guy. Okay, does that make sense? Is it new to you?
It's different.
It's different.
No, it's not new, it's just
Okay,
different.
okay, so then at least we get onto the same page with the way I do stuff, because this generalizes later on.
Yeah.
And I don't mind it if you do it differently, just get the right answer, please. Okay, so you can use whatever method you like, just go through and check it. So now what we have is I have an expression for my tangent in terms of S. Okay, and I assume lambda is implicitly a function of S. And if I plot this tangent over here, I get my unit vector. Okay, so now the next step is I want to work out the normal vector with the arc length parameterization. So I want to work out the quantity dt ds. Okay, and so once again, dt ds is the derivative of ts with respect to lambda divided by c prime over lambda. Okay, and that is equals to, if I just write it out, remember our definition of kappa and n of s is, I can say that's equals to kappa times n of s. Okay. And I can basically take this guy, differentiate with respect to lambda, and divide it by this factor c. Okay, and then I get the whole big thing, and then I can separate it out into the norm and the unit vector. Okay, so if I basically take this guy, differentiate it with respect to lambda, and then divide by that, what I'm going to get is this expression, and I simplify it. I get this expression that's basically the product of a unit vector, which is this guy. Okay, and that unit vector I've plotted here in brown, and kappa of s, which is my curvature. Okay, so it's once again, I've given you a non-trivial example. Go and make sure you can actually get it to work. Okay, because that tests your understanding. So this curvature kappa of s has the meaning that it's the norm of dt ds, but it also has another very useful interpretation, in the sense that associated with curvature there's a radius of curvature that's 1 over the curvature. Okay, and if you then go about and you plot a circle that is tangent to that point with a radius of 1 over the curvature, you get what they call an oscillating circle. So what you do is you want to plot a circle that has a radius 1 over the curvature, okay, and its midpoint is basically along the normal vector. And if you do that, you get the circle. Okay, and this circle is something that they call the oscillating circle, with radius r of s equals to 1 over kappa of s. Okay, so you've literally taken your curve. The first approximation to the curve is a straight line, which is your tangent plane. And the next thing is this curvature, which is basically you fit a circle to your curve at a particular point. Okay, you know where the midpoint is relative to the curve that's given to you just by the normal vector. And the magnitude of the circle is defined, or the size of the circle is defined 1 over the curvature, 1 over kappa s. Okay. And now there is a number of results, which I'm actually not going to derive, but it's a completely different way of looking at a curve. So if somebody told you, I've got a curve that's parameterized using the arc length, in other words, a distance, and then they give you the curvature as a function of that distance, then you can actually prove that it's possible to reconstruct the entire shape of this curve. Okay, you don't need any more information. You might get the orientation wrong, you might rotate it or something like that, but the actual shape of this curve is entirely determined by the curvature. That's all you need to actually get it. If somebody gives you the curvature as a function of arc length, you can reproduce this curve. Right, so that's 2 dimensions done. There's basically one fundamental function of arc length that determines your entire curve, and there's a very strict geometric interpretation for what it is. So you can see now, suppose you traverse the curve, suppose we go to this point over here, right? You're once again going to have your tangent vector pointing in this direction. Your unit tangent vector is going to have a size 1. Your curvature over here, or your normal vector, is also going to have size 1. And then your curvature over here is it bigger or smaller than that thing?
Bigger.
Yeah. No, smaller. It's less curved. Okay, so it's less curved, so your radius of curvature 1 over kappa is going to be bigger. You're going to have
the radius is bigger.
Yeah, the radius is bigger. You're going to have a much bigger curve fitting over there. And if you go to this kind of extreme point over here, you're once again going to have your tangent vector pointing in that direction, your curvature or your normal vector pointing in that direction, and then you're going to have a radius of curvature that is
Curvature that is going to be larger,
Yeah.
radius smaller.
radius smaller, so you're going to have a tiny little circle fitting in there, and you all of this you can actually calculate with this formula. Okay. So, just context, those GR orbits, I tried to look at it using this and I didn't get anything out. If it's something you want to try, you're welcome to. Right, so with the paper folding, we have a game of knowing two-dimensional curves and then wanting to see how they transform into three-dimensional ones. And before we do that, let's now look what's possible in 3 dimensions. So, yes?
I maybe stop here.
Okay.
Class.
Okay, so, yeah, shall we stop there and then go on tomorrow?
Yes.
Okay, right.
I don't know how long this slide is.
No, it's longer than 5 minutes, you're right, so thank you.